Section 15.4, Heterogeneous Equilibria. In a normal situation with equilibria, you're going to have a concentration change of different materials. So if you were to have a regular concentration of, remember you have some kind of a concentration, some kind of a coefficient of A as a reactant, some kind of a coefficient of B, and it's yielding some kind of a coefficient of C, some kind of a coefficient of D. Your concentration is based upon the concentration of D, and that's what molarity concentration raised to the coefficient, and C. I should put C first. C raised to the C, all that on top, and then concentration of A raised to the A, and concentration of B raised to the B. Well, in the case of heterogeneous means there's different phases. You've got solids and liquids and gases all kind of at the same time. You can have an equilibrium established between a solid and a gas. So you can have a solid that breaks apart into a gas, or you can have a solid and a liquid dissolving and making a gas, or making another aqueous solution that's going to change. But anything that is pure substance doesn't really have a concentration, because its concentration would simply be the amount you have over the amount you have, which is the same, and you'll always end up with 1. So let me give you an example from this slide. Okay, so in this example, you've got some limestone, which is calcium carbonate, and it will break apart into carbon dioxide gas and lime. Lime is what you mark a football field with. So that calcium oxide is a solid. Well, that solid is going to be essentially a constant, because anything that's a pure substance that's not an aqueous solution or a gas, it is not going to change at all. So it will maintain essentially a constant position. So you can simply replace the concentration of the calcium oxide with a number 1. Also, limestone is a solid substance, so it can be a 1. So if you have something here to where the equilibrium constant is equal to 1 times the concentration of carbon dioxide gas divided by 1, well, it's just the carbon dioxide gas. Well, the easier way to say that is if you have a pure substance, either a solid, that's an S. You can see that easily on a balanced equation. You've got S, that's a solid, or liquid, L. Then you're not going to include it in the equilibrium expression. You're only going to include gases or aqueous solutions, and that's all. Well, that's easy. So essentially, you just leave out everything that is not an aqueous solution or a gas. So if it's G or AQ, you're going to include it in the equation, and if it's an S or an L, you leave it out. So in the case of K sub C, you're going to leave out both of the solids, and so your K sub C is only going to be based upon the number of carbon dioxide moles that you have. Likewise, if you want to express, since that is a gas, you want to express it in pressure, it's only going to be equal to the partial pressure of the carbon dioxide. So on the right, you've got a kind of a picture of an experiment that they've done. So you've got some, let's say you've got some limestone here. That's the calcium carbonate. It's the pink stuff. Let's say you have lots. On the right, I've got lots. I've got a lot of that, just a little bit of the lime, or I have a lot of the lime and a little bit of, remember, you can go from either side. It doesn't matter. You're always going to reach an equilibrium. The pressure of the carbon dioxide gas, the carbon dioxide is above it, is going to be the same. You're going to make the same amount regardless of where it is, and so it's only based, so this constant, this equilibrium constant, is only based upon that something that can change, and that is the gas pressure or the concentration of a solution.